Welcome back to another SuperMagnetMan video. We are delighted to present this time on pyramids. At SuperMagnetMan, we are insanely curious. And one of the things about our curiosity is our customers keep feeding our curiosity with more and more questions. And they ask questions and we say, oh, that sounds interesting, let's find out. So I set up a procedure and an experiment to try and figure out how can we answer that question and how can we learn more about magnets, and then we start trying to figure out how we can share that through these YouTube videos. Today we're going to be talking about our pyramid magnets. Pyramid magnets are something that a lot of customers like, and they think about the pyramids from Egypt and all kinds of other things about pyramids, but magnet pyramids are different, and we want to take a minute and talk about them. This particular pyramid is the biggest one we have now. In the past, I have had 4-inch pyramids made, 4-inch square on the base and 3/4-inch square at the top and 4 inches thick. Incredibly powerful magnets. But this particular one is our standard N52 magnet. And this one you can see is 2 inches square on the base, which is 50.8 millimeters, 1 inch square, which is 25.4 millimeters on the top, and then it's 1 inch thick or 25.4 millimeters thick. So we're going to take a look now at what the readings are when we look at a pyramid like this. We look at a pyramid like this, and in the center, on the top, is 5,850 Gauss. In the corners, it jumps to 7,510, 7,400, 7,580, 7,540. We're going to see why those readings are what they are in just a minute. But my whole fascination with pyramids did not start with making one that was strong on the top. My customer, that back in 2001 or 2002, whenever that first one was, what they were really looking for is how can I get a nice homogeneous magnetic field. They wanted as little gradient as possible, plus or minus 50 Gauss is what we were looking for. And I knew that with a standard rectangular magnet, no matter if it was like 2 by 2 by 1 inch thick, that if I took one like that, the field lines go around like this and the flux drops dramatically. So I really didn't have but maybe a 1/2 inch square in the middle, and they needed at least a 1 inch square. So what we did was I thought about, what if I turned the pyramid design upside down? What's happening is, as we're moving more to the center of the magnet, it's getting thicker. Since it's getting thicker, it should maintain a fairly homogeneous field across the big side. And that's what we see. In this one in the middle, it measured 4,300 Gauss. As we went right underneath this 1 inch point out here, 4,220, and we come down right under this one, 4,260. So you can see it's not even plus or minus 50 Gauss, which is exactly what we needed. And so the pyramid design worked from that standpoint. Since then, everybody has come up with applications dealing with how we make them stronger. And we're going to look at some ways that can help us make them even stronger. But we'll take a second and look at our 1 inch pyramid. This one is 1 inch square base, 1 inch thick, 1/8 inch on top. If you look at the top of this one, it's 8,540 Gauss in the center compared to 5,800 over here. And then we have 4,710 in the center here and 4,200 on the edges, because we don't have a large area across the top, and so we have a very small one, so it stays pretty good right in the middle, but we wouldn't have an even field across the bottom based on this design. We also have some smaller ones. We have a 3-sided one. This is our triangular pyramid, which has a 10 millimeter long base and a 6 millimeter long top. And we get 5,220 Gauss in the center of this one. It's 10 millimeters thick. Now this 4-sided pyramid is also 10 millimeters on the side, and it's square, and 6 millimeters on the top and 10 millimeters thick. And we get 5,740 Gauss on the top of that magnet, which allows us to have some projects and some applications for customers that really need an intense magnetic field in a very small area, but they can't use one of these giant magnets. And so this works out great for them. Now what we're going to do is take a look in detail of what really happens. What do the magnetic field lines look like, both from a magnetic modeling software standpoint as well as an actual model that we've made to help us better see the magnetism in a pyramid-shaped magnet. To understand our B-field plot chart we're going to look at in just a minute, let's first understand this diagram. What this shows us is B, the total magnetic flux density, is equal to the H, which is your magnetic field strength, and the magnetization, which is M. And this is what we're looking at when we see it. We're going to be seeing this graph on the left. What we're looking at is a pyramid magnet, and this is showing us the B-field plot. As we look at the upper left-hand corner, where you see at the top, that Gauss reading would be in the 7,000 to 7,500 range. That's where the dark red is. As we move to the center, we see that the Gauss reading is around 5,000 to 5,500, and you can see that it dips quite a bit in the middle. As we look at the bottom part of this in the center is much lower. It's in the 4,000 to 4,500 range. Along the sides, you can see that inside the magnet material, you're getting a pretty high strength, but just outside of the magnet itself, it's quite low. It is in the 3,000 Gauss range. It's hard for us to get a reading on this because the actual magnetism is more or less parallel to the surface, not perpendicular, so it's hard for us to get just a straight reading with a regular Gauss meter. As I mentioned, we're going to take a look at our molded. These are the actual molds that show us exactly where the lines of magnetism go around the magnet. We want to take a look at some things here. One is, notice how the flux is coming straight off in the center. You can see the lines of flux that are going straight up. As we get to the edges, you see how it's beginning to curve because the North Pole wants to loop all the way around and find the South Pole. And you can see as we get closer to the edge how it is coming off more and more at an angle. So you're going to have, if this is a South Pole magnet, you're going to have lines of flux where you're going to read South Pole pretty much over this region. But as soon as the flux starts turning down, we read the opposite pole. So right over here, you'd be reading, even though you're above the South Pole over here, you would be reading North Pole with a Gauss meter. Now we're going to take a look at it from the top. And as you look at it from the top, you can see that as this line of magnetism is coming straight out, this is going across the magnet this way, we can see in the middle down in here that it is coming straight off, and it is going in both directions exactly the same as we saw from the sides. To better understand how magnetism travels through a pyramid, we first have to understand a key term in magnetic materials and the manufacture of neodymium magnets. This term is magnetocrystalline anisotropy. And this word means that the lines of magnetism only magnetize along a preferred axis. When these materials, neodymium, iron, and boron, form together under the right circumstances, they form a particular crystalline shape. And the magnetic domains are oriented relative to this. So when they apply a magnetic field early in the manufacturing process, it orients all the domains to point in the same direction. Why is that important? Well, let's take a look. Most of the people that think of a pyramid think it's doing this. They think that the lines of flux are focusing in to this smaller cross-sectional area from all directions. And when you look at that logically, you think, well, why wouldn't it be doing that? And we'll talk about that in a second. That's where this comes in. But if I took this and I said, okay, if I'm averaging 4,300, even if I was averaging 4,000 Gauss across the whole bottom of this magnet, it's 4 square inches compared to 1 square inch. Why don't I get 4 times the power out of it? Why don't I get 16,000 Gauss at the top? Here's where that comes in. Because what's really happening, because of this feature, all of the magnetism actually looks like this. And so what happens is, when the magnetism gets to the edge, it loops around and completes the circuit so it goes back. One of the things that we look at in magnetism is magnetism prefers to travel through magnetic material or ferromagnetic materials. It doesn't like traveling through air. Now, if your curiosity is like mine, you can't see the information on these two pyramids and not wonder what would happen if we put the two together. And of course, the dimensions obviously indicate we intended for them to go together. But let's take a look at how we put them together so we don't break one of them, and what it does to the Gauss reading once we've done that. So I start with the magnet, then I'm going to put the wooden wedge on top. Now we take the smaller magnet and we're going to let it pop on top. You see how it pops on top. Now we line it up and start sliding it off, go all the way down, pull the wedge out. Now we have a magnet that is a 2-inch square base, 1/8 of an inch top, and 2 inches thick. So let's take a look at what that did with our Gauss reading. I am getting 9460, 9430, 9480, just right in that 9400 to 9500 range. So we're getting almost a Tesla out of this magnet combination. But now we see what you get when you put these two together. And then we're going to follow that with some of these models. We have made a lot of models to create some that let us see specific things. This is one of a pyramid magnet just in free space. And then we have a pyramid model where they are repelling each other. And we have a pyramid model where they are attracted to each other. And looking at these close up, we're fixing to zoom in on and point out things for you to notice to see how magnetism is traveling around the outside of the magnet. Now we're going to take a look at the bottom of the magnet. And as you look at the bottom of the magnet, you can see across here how the flux is not moving and not as curved as it is up here. You see a greater area where you are fairly straight coming off, maybe a few degrees, 10, 15 degrees at the most, until we get out to here. And then you see it begin to curve and form the lines on the edges here. We can see the same thing when we look from the end, and you can see all the way through and across the magnet, it would be giving us the same pattern. And if we look carefully on the edge, you can see on the edge how it is really getting a low angle here. So it's coming off, going around, looping back to this end of the field. Now we're going to take a look at the sides. Notice that along the sides, what I was talking about, you can see that the flux is coming all the way up the sides. It's actually parallel to the surface here, so we're not getting any of our flux here that's going to participate in the reading up here. This material is just creating a circular flux pattern. It is not coming up here. It's just parallel to this outer surface, and you can see that with the lines coming out here and going down. This is because of that anisotropic nature of the neodymium magnets. One of the things that everybody likes to look at on magnetism is how does magnetism look when it's attracting? This B-field plot of two pyramid magnets facing each other, and they are attracting, so you can see how the lines are going to look with this. Now we're going to take a look at what it's going to look like with our model. In between the magnets, you can see that in the center we had a really strong attraction. All of this area, you see just straight lines across. If you were wanting a very homogeneous field, you would want to take two of the pyramids like this, and this would give you a very homogeneous magnetic field in the center, and it would probably be in a 6,000 or 7,000 Gauss range, about 0.7 Tesla. We can make it bigger. We can add large 2-inch cubes on the ends, and that will pick up the Gauss reading some, but this gives us a very strong field right in the center, and you can see how the lines of flux look. Now what we see happening is because this opposite poles, north and south, you can see that on the corners our flux is no longer running and making the circle. The lines would be arcing out like this, and we're connecting it. Therefore we're getting more use of our total flux than we do otherwise. Also, you can see that it doesn't affect the end because the flat end is still very homogeneous across this end as opposed to what it looks like here and the way it looked in a single magnet in free space. Now, if we look at the end lines, you notice in these straight magnets you saw a lot of flux that was parallel. Well, we're all the way down to about 1/3 of the way up from the base. You can see we now have a very small region where it's parallel to the surface. We're actually getting some flux coming out like this, which is looping around, and we're getting more benefit out of this when these two are attracted. Now we'll take a look at the B-field plot of two pyramid magnets that are repelling each other. And you can see in the center we have a null field. That blue means it is pretty close to zero. You see how the lines are coming out just a little bit and then they turn and separate from each other. This is what we will also see in the model. Our repelling magnets, you notice most of the field disappears in the middle, which is what you would expect. In the dead center between these two, we should have zero Gauss. All of the flux is canceling each other out. What's happening is you can see the lines of flux now are coming off, and you get a short stack of flux that's wanting to come towards the center, but then it begins to turn because the repelling fields meet each other. Now you get a lot more concentration around this edge out here where the flux is coming off, and it's being flattened by the other field. Again, our bottom still looks very good and homogeneous across this area. Earlier in this video, I mentioned our magnet stacking technique. This is something we developed, I guess it was like 15 years ago, and I developed this because of looking at what the magnets do as they go from one stack to another. And when I looked at this, I noticed that just like we've already seen in the flux patterns, we're able to see that the magnetism wants to loop on these corners. Out here, it is going to form a circular loop, and you pretty much lose that. So there's a set distance that I like to come in, and I've tested this to come up with the right distance to try and optimize this. And we come into this point, and now the flux that's in this region that was a very high intense concentration of flux says it'd rather travel through another piece of magnet material than circulating in air. So we see a lot of this flux will loop in and go into this piece here. Now it shrunk the surface area. Now the flux that's out here will once again loop and go into this one. And each layer is reducing the cross-sectional area substantially by a different amount each time, all the way down till we get this 3 millimeter square surface area. And on the 3 millimeter square surface area, we're reading over 9,900 Gauss. We've taken it from a magnet that had 5,830 Gauss in the center. But by adding these stacking magnets, as you'll see, when we put the Gauss meter on this, we're able to get 9,930 Gauss. That is just 70 Gauss short of a Tesla. You can push this that weighs about 1 pound into having you a very, very small 1 Tesla field at the top of it. And this is a technique that many people have used and many of our customers have used when they need a really high static magnetic field in a very small area. We use this stacking technique to really help push that flux up to where they need it to be without needing an electromagnet or a superconducting magnet to just get up to that range. Now, we have taken this to even higher levels. Our last thing we want to look at in the pyramids is looking at our giant C magnet. This is something where we used 2 pyramids with 2 large magnets and an assembly to put it together with the stacking magnets, and we're able to push this to about 2.5, 2.6 Tesla with 1 static magnetic assembly. And we've mentioned this, and it's got its own entire video where we talk about this particular magnet, but I wanted to just show you this is how we have learned to continue to change and challenge ourselves with this pyramidal design and focusing the magnetic flux and the basics that we understand, how it all comes together. We're also driven by all of our customers who keep asking for various applications. They keep contacting us. Can you make a magnet that does this? Can you make a magnet that does this? And at SuperMagnetMan, we always try very hard to get where they can. We get as creative as we can with both pyramids, hallbacks, and a wide variety of other magnets to help you understand how magnets work and for us to try and help you achieve your goal for your application. So if you have applications for magnets that require high intensity fields, that require a focused field, or require things like this, don't hesitate to call us at SuperMagnetMan. We look forward to helping you develop a solution for your application. Thanks again for watching. Look forward to you with the next video coming up soon.